right, so now we are working on example number 8 for lesson 10. We're looking at a child sledding down a incline, and we want to know what is the speed of that child at the bottom of our incline. When we're looking here, we have more than one force present. So if we're looking at the forces here, it is made up of gravitational. So we do have the UG because we're seeing that change in height. And we also see our frictional force. Remember that frictional force is responsible for work done by dissipative forces. So as a result of all of this particular thing, we are going to see the work dissipative is equal to our change in energy. So we're going to go ahead and start with the frictional force. Frictional force, as you know by definition, is equal to our coefficient of friction times the normal force. Because of all the different kinds of problems we've done previously, we know that our normal force right here is going to be equal to this portion of our weight if we break it into components. So that normal force is going to equal that mg times cosine of 28 degrees. So now we can go ahead and substitute that into where our normal force is for our friction. Is equal to our mu times mg times cosine of 28 degrees. We know our mu k, it's given to us in the problem. We know our, we know our mass, and we know gravity. So we can see our frictional force is equal to 0.20 times 35 kilograms times 9.8 meters per second squared times cosine of 28 degrees. So our frictional force is 60.57 newtons. We're not just interested in the frictional force, we are interested in the work dissipative, so that work done by the non-conservative force is equal to that frictional force times our displacement times the cosine of the angle between those particular forces. We are moving down the hill and our frictional force is up the hill, so we are going to see that the angle between those two is 180 degrees. Remember, cosine of 180 degrees is -1. So our work dissipative is equal to that frictional force, which we just found was at 60.57 newtons. Our displacement is given in our diagram and in the problem, 65 meters times that -1. So we do get this particular number for our work done by dissipative forces. So the next thing we need to build is what is our final energy and our initial energy. We're going to go ahead and set that our height initial is some particular non-zero value. Well, we need to find out what that is, because we are looking at the fact that we see this change in height right here. We know the length of our incline. We know the angle that incline is at. We can go ahead and use that to find out what is this length here. Because it's the opposite side, we are going to be looking at sine. So the sine of theta is going to equal that 65 meters divided by my initial height. Right? Remember that theta is the 28 degrees of our incline. So our initial height is going to equal 65 meters divided by the sine of 28 degrees. Nope. Sorry about that. This is upside down. Sorry. it's actually going to be the sine of theta is equal to my initial height over 65 meters. I apologize for that. So my initial height will equal my 65 meters times sine of 28 degrees. Sorry, my handwriting is getting a little messy. As a result, my initial height is 30.5 meters. So this is right here is 30.5 meters. That go ahead and lets us know that my final height is 0 meters. So our final energy is equal to our 1/2 mvf squared plus mghf. We will have a speed at the bottom of the hill, but we won't have a height, so this particular one goes away. Our initial energy is going to equal that 1/2 mvi squared plus mghi. We are starting our child from rest, so our initial velocity is 0. As a result, we do get final energy, initial energy, and our work dissipative. So equal to my 1/2 mvf squared minus mghi. So when I skip a little bit of algebra and switch to what I'm solving for, which again is my final velocity, we do get this. All right. From here we can plug in everything that we know. As a result, when I plug all that into my calculator, I do get a final velocity of 19 meters per second.